Good morning. This is Antonio Malarino. Hopefully you are seeing in your screens the full first slide of the presentation. The topic today, after we got so many questions last year, is to discuss a little bit tissue testing for micronutrients and mainly P and K. I was saying that soil sampling and testing is common, and the potential sources of error are well known. See, soil sampling at the field is the most common source of error. We have the spatial variability, the number of samples to take from a field or from a grid cell, the number of cores per sample, and so forth. Then we have the variation with depth. We need to have sampling depth consistency. The sampling timing is very important for nitrate, of course, and sometimes also for pH and potassium, not as much for some of the other nutrients. Then we have the subsampling at the field or at the laboratory, when you get soil to fill the bag and send it to the lab, and then the lab grinds the entire sample or not, and so forth. Then we have the analytic and error. And then, of course, there are a trillion soil test methods out there, but there are a few that work well in our soils, and some in some soils, some in others. So the key issue with all this is that soil tests are indices, So we need the field calibration we get response to a specific depth. So that way we give a meaning to the ppms that we see there in the results. Now we have all this in our general guide for crop nutrient and limestone recommendations in Iowa, PM 1688. You can get them, in those two links that I put there in the extension store or in our soil fertility website. So in there we have guidelines for pH and liming, for P and K, with interpretations for several soil test methods. And for micronutrient, this is important, we have only for zinc and for corn and sorghum. That's the only micronutrient that we have that we cannot trust after many years of research. And our interpretations are for the DTPA method, okay? Now, why we're talking about tissue testing? Well, many people believe, and I was one of them, that a plant could be a better sampler than a soil probe. So we could eliminate at least some of the effect of the very small scale variability in the field. Now, this happens when the root system is already somewhat developed. If you have a plant, V2, V3, V4, V5, maybe that's about the same that a probe in terms of soil exploration. Now, the other thing is that people believe that with tissue testing, it's easier to know what we are measuring. See, with the soil, we are having all these different methods, different extractants, trying always, mostly empirically, to see what is the amount that is available there for crops. Now, people believe that that's much easier with plant analysis, but it's not the case, okay? The main reason is that the nutrient concentrations in plant tissue changes a lot due to accumulation in different plant parts, remobilization, when for example, some nutrients take the nutrient from the older leaves to the new leaves. And then there is all this concentration of dilution of the nutrient that is absorbed in the dry matter, okay? So there are changes as plants develop over time and also between plant parts. The nutrient concentration, especially for some nutrients, is strongly affected by growing conditions, for example, temperature and mainly drought. The other thing is that with high nutrient supply, plants usually can absorb higher levels than needed, okay? So there is like a luxury accumulation, as some people say, in different tissues. And this accumulation may be different in different tissues, in different leaves, in different leaves in the top, leaves in the bottom, etc. And then, because of this reason, very high levels of some nutrients, not many, can be toxins, if they are too much being absorbed. And so because of all these things, we are in the same boat as we are with soil sampling and testing. We need field calibration with yield response in order to see how the nutrient concentrations in different times in different plant parts relate to the nutrient sufficiency and the potential yield response. Now, for soybean, we had no these field calibrations for tissue testing until very recently, until about 3 years ago. And for corn, there was some data over the 70s mainly, and then something I did in the early 90s, but the data was insufficient to develop interpretations, okay? Now, in Iowa, when we're talking about soybean, there are essentially two nutrients that nutrient deficiencies are fairly common, and we can see, and one is the potassium deficiency, in the top, and then the iron chlorosis. See, in calcareous soils, the iron gets tied up, and this is not a problem for corn, but soybean is sensitive to that. And then there are wide differences between varieties. Breeders have been trying for a long time to address this issue. So we need to go, before we get to start showing data and guidelines, I'd like to discuss a little bit what in the world we mean by, sometimes we talk about critical concentration ranges, sufficiency levels, and so forth. So let's look at the chart on the left first. So as the nutrient concentration increases, then of course, if there is a deficiency, crop yield increases. So we have this part of the response curve where there is a deficiency. So as the nutrient concentration increases, then yield increase. Then there is like a small curvilinear thing here, and then there is a plateau where there is a wide ranges of concentrations where if the nutrient concentration increases, the yield doesn't increase anymore because the plant has enough. And then, as I said, with some nutrients, if there is an excess, then there could be some yield decrease. Now, this is easy to understand. What is sometimes confusing is the terminology that we talk, and the researchers talk, or even extension, or some consultants out there. We researchers prefer to talk about critical concentration range. And I give it just an example, theoretical here, that normally is a range of concentrations, and this is valid for soil too, okay, for soil test, where we are there, where we are from almost enough for maximum yield to maybe a little bit more, okay? I mean, we know that there are errors in sampling, error in analysis, errors in recommendations. So this is what we call the critical concentration range, okay? Essentially below that, there is a very high probability of a yield response to fertilization. And when we're above that, then the need for fertilization is very unlikely, okay? Now, when you talk out there, you look at farm magazines or all kind of things out there, people, especially for tissue testing, people talk about sufficiency levels, okay? This is not wording, is not used too much for soils, but it is for tissue testing. Okay, so what happened is that years ago, some people started talking, especially because of the uncertainty in terms of what is the critical level, to talk about a sufficiency level range, Now, the problem is that different people, different states, different publications, it's not entirely clear what in the world they mean by when they talk about a sufficiency level, okay? So what is happening is that when you see something, you see, and I put these blue dotted diagonal lines here to give an example. Are they referring to the entire, this plateau region when a change in nutrient concentration doesn't increase yield? Or are they talking about part of it? Or are they talking about a critical concentration? Okay, so in most of these interpretations out there, they may not be looking at the entire flat portion of the curve, but they may be referring to part of it. Like, for example, from where the nutrient produces the maximum up to maybe a little bit higher. So that is sufficient, okay? Because below that, there is a likely deficiency, and above that, either is more than enough and doesn't create a problem, or if there is much more than that, it may create a problem, okay? So, especially with tissue testing, there is much confusion about this, okay? The critical concentration range or the optimum range is not the same as the sufficiency level, okay? Now, in the chart on the right, I explain a couple of things, an example with phosphorus and potassium, to explain some of the things that may happen or not when we are talking about nutrient levels and the relationship with yield and nutrient concentration. For example, if you look at the potassium, the red curve, okay, as the soil test level or the fertilizer rate increases, then of course the concentration of potassium, in the red increases. Now what happens? If we assume that this is the level that is actually needed, this vertical dotted black line, then if we apply more than is needed, or there is higher levels, then still the potassium in the vegetative tissue keeps increasing. So we talk that there is very likely and high luxury uptake of potassium into vegetative tissue. This is not the case in grain though, okay? It's mainly in vegetative tissues. Now, look at phosphorus. In this case, after a certain level, the plant stops absorbing phosphorus. So now this level is usually a bit higher than the amount needed, okay? But then shuts off. See, and there are different physiological reasons for that. So what happened? If we are, the nutrient concentrations are in the deficient range, okay, it's no problem. We should see low, or higher concentration depending on the supply. But when we are close to the level that determines maximum yield, it may happen with phosphorus that you may have, 2-3 times more phosphorus in the plant than needed, but still the concentration doesn't increase as much. So you cannot see it, okay? So it's not clear often, especially with phosphorus, is that level, okay, is that okay? Or really it's much more than needed, but we cannot test it and it doesn't do any problem because usually excessive phosphorus doesn't create a problem. Now in potassium, it's okay, you see. See, in potassium, we can detect a deficiency, but also can detect an excess over a certain critical level, okay? So these are things that, and then vary with the different nutrients. But see, people need to understand this. So then they understand better when they are looking at these sufficiency levels of tissue test and when they are going to make a decision about fertilization. Now, let's start with P&K. As I said before, the recent research targeting essentially tissue testing started not many years ago. So there were here in Iowa phosphorus trials from 2009, 2010, and then until 2014. The plots were, or the strips were with this. The soil pH was very low to very high. The treatments were broadcast or banded. So we were sure when we had maximum yield. And we have 32 trials for corn and 34 for soybean. Now we are talking about soybean today. Then for potassium, we have trials, but we look at this from 2003 until 2014. And again, We have all these treatments. We have 66 trials for corn and 52 for soybean. And I like to acknowledge here the people that help us, with funding for this project. Now, based on these results, okay, in June of 2018, we put together with Dr. John Sawyer the first Iowa interpretation, tissue testing interpretation for phosphorus and potassium. There has been none, okay? Other than the nitrate corn stalk test, there have not been any guidance about tissue testing, okay? So this is in this publication. It's available in the publication store for free to download, and it's also in our soil fertility website. Now, I put here the main thing in that publication. The publication shows these interpretations, give some background, and also show some data that I will show next. Okay, so I'm showing here table 1 that shows phosphorus, the interpretations for corn and soybean, and then potassium for corn and soybean for 2 sampling times and tissue parts sample. We sample and have this calibration with response for sampling of the entire plant at the V5, V6 growth stage. That's a stage that many people sample out there over the world. And then later at mid-season, at initial reproductive stages like R2, R3, trifoliate soybean leaves, the top leaves, and in corn at silky, the EL leaves. So here we develop these interpretations we call low when the nutrient levels in whatever plant is being sampled is less than these numbers here. We call sufficient at the range, this range. And I will show you what is that we mean by that. It's close to what we consider critical concentration range in the scientific circles. And then when the concentration is higher than this level, then it's high, which that means that fertilization is not needed, the supply is okay. But I mean, in general, with very few exceptions, with P and K, there are no yield decreases, except for mainly for potassium, if there is a salt effect or things like that. Okay, so essentially now we do have then interpretations for tissue testing for both corn and soybean in Iowa that are in this publication. Now this is the data that we use for that. Each point there in these graphs is a trial in some year, in some different fields. And what we have here is how the plant concentration of V5, V6 affect the soybean yield response and leaf phosphorus at the R2, R3 relate to the yield response. Now, this is not bushels, this is relative yield response, okay? So 100 means that further increase in the concentration does not affect yield within some error. That's what it means. Now, I put here 2 vertical dotted lines, okay? So we determine these borders for the sufficient range. For example, for plant P is 0.33% to 0.41% using fitting different response equations and models that are normally used. And this is our criterion to define what that is, you see. It is the lower boundary means that below that, there is a very high probability of a yield response in both tests, okay? When we are in this range, the likelihood of response is not that good. If you average all these points within that sufficient range, there is, essentially it's about 100. And of course, after that, there is an increase in the nutrient concentration, but there is no yield increase. Now, we included this in the publication, so people really know what do we mean by that. Okay, what the heck you mean by sufficient? Okay, this is what we mean. This there. Okay, you may agree or not, but at least this is there, and it's very clear what was our criteria in order to define this. Now, in terms of is4P, the plant test or the leaf test, the plant is on the left, the leaf on the right. Which one is better? It's not that clear. Seems that the plant would be a little bit better here because there is less dispersion, you see. But this is the case, you see. For example, if you have a concentration of 0.25% here, you may get a huge response or nothing from that. See, this is the issue with all testing. I mean, the tissue testing or soil testing, okay? Now, this is phosphorus and this is potassium, see? The criteria was about the same. And this is the 1.89% to 265 is our sufficient range for the testing plants at the B5, B6 stage, sorry. And for the leaf potassium is 1.80 to 245. Okay, so now you fully understand when you look at this table with the interpretation, then you know what we're talking about. Okay, now note the dispersion of points, because of course ideally we should have a curve, you know, with all points aligned in one curve, but that's not the case. Now, this is what we have with phosphorus, and this is potassium in soybean. Now, look at soil test. I just put some of the correlations that I have been showing for years for corn and soybean, see? So then you can say, okay, is this better? Is tissue testing better than soil testing? No. In fact, maybe worse. For potassium, this is the data we have that support our current interpretations for the dry test. It's about the same, you see. See, this is the dispersion of the points, where we get a maximum, etc. It's about the same, or maybe a little bit better than what we see with the soybean, with a tissue test. This is the potassium. Oops, sorry, my mouse is playing tricks on me. This is the soil test, the moist test for potassium in corn and soybean, and it's a bit better than the tissue test in terms of defining when is it that we need or we don't need additional fertilization. So, what is the usefulness of tissue testing for P and K? Okay, these are my conclusions, and I guess Dr. Sawyer agrees. It's not better than soil testing, okay? There are unclear differences between testing early, say at the B5, B6 stage, or mid-season. Now, if you look at the graph, you will see that the concentrations are widely different. They are higher in early stages and lower in late stages. So the testing at early stages, and that's why I did much research on this, is because I believe that testing at this time, it would be more useful to correct a deficiency and alleviate the yield loss for the tested crop. See, when we sample, you know, at the reproductive stages, be corn or be soybean, I mean, for P and K, you know, on micronutrients, not much you can do. The damage for the yield is done. So that's why I believe that testing early, if somebody wants to use that test to see if they can make a correction, say with foliar fertilization, then it will be useful. Now, I still think that the tissue test for P and K should be used in conjunction with soil testing. It's not one or the other. And I believe that perhaps I could not prove that. I included trials with banding, P and K high rates, and it's not entirely clear, but we know that there is especially very high small-scale variation when people band the primary PRK rates, which in Iowa really doesn't make much sense. We have plenty of data that is not needed. Clearly for P and for K, maybe in no-till, strip-till, when we have dry seasons, or in rich till, then there is not much anymore. So when there is special situations where the soil test result may be more uncertain, how it really applies to the area sample, then maybe having, tissue testing could help, understand and then see what is the situation there. I see the other way that this could be used is, which many people do that, is when they see something different, say green areas, yellow areas, something like that, bad or good in a field, then you can do both soil and tissue testing, even though we may not have the calibrations for whatever time of the year you will be doing this. But if you do both, then you can have an idea what's going on between the bad and the good areas. Don't do just the tissue testing, because that could be very misleading. Okay, now switching to micronutrients. I just put here a list of the micronutrients on the left and the abbreviations that we normally use. And I put in yellow the nutrients that, for which soybean is particularly more sensitive than corn. It is iron, manganese, and molybdenum, okay? Now, many Iowa soils have high supplies of macronutrients, and you will see, I will show some results. Now, the iron deficiency is common in calcareous soils. So you go to north central Iowa, some spots, as I showed a picture before, or western Iowa, then there is this iron deficiency. The molybdenum deficiency, it has been documented years ago in the 60s in southern Iowa, in soils that were extremely acid, pH 5 or less. Okay, but then of course, a farmer should not have this pH for any crop, corn, soybean, or whatever it is. So it should lime, and the liming really eliminates the molybdenum deficiency. So that's not an issue. Now, sulfur, many people are confused and include sulfur as a micronutrient. It's not. Sulfur is a secondary nutrient, and sometimes it's needed in Iowa for corn, soybean, or alfalfa. We have seen that. So, and I put here this publication. This was put together a couple of years ago, and it was a multi-state effort. Several states that are here in the bottom. We were together like 1.5 years to put this together. We have data, we have discussions for each micronutrient for soybean, and it was published by Iowa State. It is in the extension publication crop 3135. This is a very useful for micronutrients in soybean. It really says what we know, what we don't know, and some of the issues we have. Okay, now I started doing research in micronutrients late, mainly 2012, because I wanted John Sawyer to do it, but he didn't want to. So I put together a huge project funded by several people. I put here all the companies and the Soybean Association that help for that. So we have several foliar fertilization trials, and we chose boron, copper, manganese, and zinc, okay? Each single nutrient and the mixture, okay? Now, I wanted to work with boron, manganese, and zinc, but one company insisted working on copper because I thought that copper, the likelihood of deficiency of copper in Iowa for soybean or whatever is 1 in a million. But we included it, okay? So we have 46 plot trials, 35 water farmer fields. We sprayed twice just to be sure that each single application was not too much, but we have enough nutrients there. We apply the rates that the companies agreed we should apply, and I agree with them. And then we have 17 strip trials where we have just a mixture of boron, manganese, and zinc, no copper. So our field extension agronomists essentially work on these 17 strip trials over 2 or 3 years. And then we have some trials where we apply to the soil. We did this in corn and soybean rotations, but I'm just talking here about the trials for soybean. We have 12 trials. And then here we have again, single rates of boron, manganese, and zinc, no copper here. And we put single nutrients, either banded 2x2 with MAP, and a mixture, either banded or broadcast, also with MAP. Okay, so the amount of phosphorus applied was the same for all. And this is what we use with boric acid, that banded high rates can be toxic. For soybean, we put a low rate banded, and then broadcast, we put 2 pounds and so forth. These are also rates that we agree with all the companies that is what we should apply. And by the way, we put sulfur, uniform across all plots. We use gypsum because some of these have a sulfur applied too, okay? Okay, so this is when we have these experiments. The red dots were in farmer fields. The blue dots were the trials at research farm. We have 6 research farms that we did work on this. I did not want to work with iron chlorosis, with iron, and none of the companies wanted either, because previous research have shown that really you cannot alleviate much the impact of the high calcareous soils on iron chlorosis. Now, while we were working on this, and they're still working on that, research in Kansas and Minnesota found that, and this is the first time that some products really have increased yield in soybean and calcareous soils. But this was seed applied. It was not foliar or broadcast. It was seed applied, this O-ADDH chelate that used to be very expensive, has been around for many years, but over the last 2-3 years, it's less expensive. Now, so when they put this iron to the seed furrow, then there is an increase. But look at the yields that they get. So without the iron, it's 20 bushels, and with this iron is 30. So there is a small response. Okay, so since then, since I found out they were working on this, I tried to work with this product in Iowa, but I never got sufficient funding from the companies to do that. So seems there is a little bit of hope, but I just want to explain why I didn't work with iron, okay? Now, we have all these trials, yields, since we work in 2012, 13 and 14, in 2012, there were some fields, a few fields that have 20 bushels, 25, because of the drought, if you remember. But in other, we have up to 74, 75 bushels of soybean. So there was a wide variation. Now, what happened? There was no response, okay? There was a positive response in one strip trial, and there was a negative response to the mixture to copper and manganese, or the mixture in soybean in the plot trials. So we could not develop interpretation. If we don't have a response, we cannot establish what is the critical level, what is needed, what is not. And this has been the common denominator for 100 years with tissue testing, you know, in soybean, here in Iowa, and other states too. So what did we do? When we were working in that publication, Crop 3135, this North Central Region soybean publication, we pulled together data, especially from trials done from 2012 until 2016 in Iowa, those trials that I mentioned, but then several more in Kansas and also Minnesota. So we worked together and pulled together all this data. They didn't find any response either, okay? So what we can do is this chart, and this is complicated, so please bear this with me. Okay, we have here the micronutrient, okay? And we work with boron, copper, manganese, and zinc. That's the ones we work. Here is the number of trials. combined across the states, 78 for boron, 56 for copper, 88 for manganese, and 99 for zinc. Okay, remember, this is soybean. Okay. Then these are the trials that we found a yield response. There was 0 for boron, 0 for copper, 1, there was a response to manganese, and then zinc, 0. Okay. This is data from all the states. And this includes foliar fertilization, fertilization to the soil, whatever, okay? Now, this is the range of critical concentrations that we observed, okay? When we analyze at the R2, R3 stage. We didn't put in that publication the small plant because the other states don't have much data about that. It's only hours and hours. So, for example, boron, we had 22 to 62 parts per million. This is the analysis, what we observed. Copper, 4 to 13, manganese, 20 to 115, zinc, 16 to 52, okay? Now, this is the sufficiency range that is published out there, okay? This is not the critical range, it's that sufficiency range that honestly, we don't have a clue what it means, but I suspect that it is that flat area in the top that I show you when an increasing concentration does not increase yield, but doesn't decrease either, okay? So this is the ranges, the published range. So now with this exercise, we have this published sufficiency range that many companies, many people refer to this, okay? What would have happened if we had used as a criterion to expect a response, the low end? For example, we say, okay, let's say that 20 is the critical level for boron, 5 for copper, 20 for manganese, or 15 for zinc, see? We still, even when this may be about the same or higher than that, we should not have expected a response in any of these, except for one site in copper, okay? Now, what happened if we have used the high end? We can say, okay, if we have less than 55, there could be a response, 30, 100, or 50, whatever, okay? Then essentially, we would have seen a response in all the fields, okay? This is the danger of this sufficiency range, okay? The criterion is not the criterion that we use for soil testing, for example, that we call optimum, some states call median, and things like that. This is the range where the nutrient is sufficient, okay? But it doesn't mean that you should fertilize, you see, if you have more than the low end, because there will not be a response, okay? So what we conclude is that, what do we do? Because there was no determination of critical level based on all the research. All these published sufficiency ranges, if you look into the data, there is no data, there is no response data backing up those concentrations, okay? So what do we conclude then for tissue testing for macronutrients in soybean? Well, we couldn't determine critical levels and develop interpretation for Iowa, Kansas, or Minnesota because there is no yield response. Okay, there is similar general lack of yield response in northern Missouri, eastern Nebraska, and Wisconsin. There are some response in some soils of Indiana and Michigan, and Michigan. They are different soils. There are many sandy soils there, and other soils that we see responses to manganese, for example, even if the soil is not sandy. So most Iowa soils have sufficient amount of micronutrients. We included one sandy soil, but was irrigated because it was sandy, and then we found out that the water supplies micronutrients. So of course, there was no response. Then we included some calcareous soil that we didn't see a response to anything. Now, we didn't try iron. So for iron, as I said, maybe this could be a hope, but it doesn't recover the yield that you get with a tolerant variety to iron chlorosis. So what do we do with these published sufficiency ranges for other regions? Well, maybe if you use the high end to decide if fertilizer or not, that would tell farmers that they should apply lots of fertilizer that is not needed. So would use the low end with caution, because apparently those low ends Yeah, below that, there could be a deficiency. We don't know, really. And after that, then the fertilization is not needed. Okay, I just have one slide about sulfur because people ask me. There is less data about tissue testing for sulfur, but Dr. Sawyer have numerous trials. If you want, you can go see this extension publication, crop 3072, sulfur management for Iowa crop production. And he had some data for corn and soybean, but it was not good enough to establish interpretation. I mean, it's not very good, the tissue test for sulfur. However, he did find, I mean, working mainly with Brian Lang, extension in Northeast Iowa, they found that in alfalfa, yes, tissue testing for alfalfa, it could be good. But you should, if you're interested in sulfur, I advise you to look at this. This publication is very good. Okay, so let's say that we find a deficiency. What do we do with foliar fertilization? Okay, I've talked about this many times in Iowa for the last, I don't know, 15 years. So I'm not going to go into much detail because the time is running. We did the last experiments that we did were for P&K, foliar fertilization. We work in the 60s. We have with Mazar Hack 66 on-farm plot trials and 8 on-farm strip trials. We try these 3 different fertilizers, different rates, spraying 1 or twice, and we found a response to P or K. We applied the P and the K together, except for this fertilizer has only K in a few trials. So across all fields, there was a response to less than a bushel for doesn't pay. And in the responsive trials, see, are the averages for 18 of all those trials that there was a response to P or K. And this happens when the soil P and K was low. So the farmer had not applied enough before planting. Or there was poor early growth or limited P or K uptake due to soil conditions, but not due to drought, okay? If there is a drought, you're not gonna fix anything with the foliar fertilization. But if there is compaction, things like that, maybe you can. And then the last experiment we did in the 2005 and 2006 with Dan Kaiser. He was my student here. Now he's a soil fertility extension specialist in Minnesota and professor. We had 5 fields. Purposely, we looked for sites that had optimum or higher soil P and K just to see if we see a response. And people was talking at the time at the fungicide, that sometimes fungicide increase yield even when there is no major disease incidence, because could be like a growth regulator or something like that. So we try all these things without the dash bars are the fertilizer and the fungicide together apply at R2 or 3. So essentially there was no response at all to the fertilizer, but we saw a response to the fungicide. And actually here UAN at the rate that we apply 3.3 gallons reduced yield a little bit. And when we put the fungicide, then it was similar to the others, almost similar. So, I mean, there was no response. Okay, what about micronutrients? Well, I already talked about these recent 45, 50 trials that we didn't have a response. Now, before that, in 2008, 2009, 2010, Brian Lang in Northeast Iowa, he worked with manganese, with or without glyphosate, and he found a response in 2018, but then nothing in 2008, I'm sorry, and nothing in 2009, 2010. And the field in 2008 was the same as 2010, and there was no manganese fertilization in between, so we don't know what happened. And then from 1990 to 2012, there were all kinds of trials with boron, chloride, iron, manganese, or zinc, and I put here some of the references. There were just no response at all. Now, in those Iowa studies recent that I told you, that there was no yield increase, there was one yield decrease. We did measure the micronutrient concentration in the grain, and it did increase. So fertilization got into the plant, but just did not affect yield. I mean, it's obvious that the microbes got in there because there were increases in the grain concentration. So I already concluded what I think about tissue testing for P&K or microbes or sulfur. Now, what about foliar fertilization? Because if you do the tissue testing and you confirm that there is a deficiency or there are obvious symptoms for some nutrient, then what can we do for this crop that you sample? Okay, so the results are not encouraging at all with foliar fertilization. Okay, having the P, the K, and the sulfur fertilization to the soil preplant is the most reliable practice. Okay, do not reduce preplant rates because you will apply something foliar. Okay, then about micronutrients, deficiencies are rare. It's just almost impossible to find a response. Now, I couldn't be in all Iowa soils. There may be some other sandy soils, there could be a response to some micro. Okay, but the problem is that not only there is no need in general, but if there were a need, maybe the foliar fertilization may be too late to remediate the problem for the current crop. So maybe that's why we don't see a response. So I think that foliar fertilization should be used as a tactical tool. Okay, don't do it across the board because it will not pay back. Target fields to increase the chance of economic return when, for example, the recommended rates to the soil are not applied, when there are obvious deficiencies during vegetative growth stages, but kind of early. I mean, if you see the deficiencies that are 1 or 2 or 3, I don't think you're going to fix anything. And then if for some reason you suspect that soil or root conditions may be limiting nutrient uptake, such as diseases, insects, compaction, but not due to drought. I mean, if there is drought, you're not going to gain anything by applying foliar fertilizer. And with that, this is I put a couple of times, this is my phone number, and this is the soil fertility website. Dr. Sawyer have done a super work over the years. I just help a bit, put in lots of information in this soil fertility website.